Good day, I am James Angelo Silipiao, and for this video, we're going to talk about radiation and propagation of waves. But before we formally begin with the discussion, let us first understand or know what are the objectives of this presentation. There are three objectives, which are first, to understand wave, electromagnetic waves, radiation, and associated phenomenon. Second is to explain optical properties of radio waves such as reflection, refraction, diffraction, and polarization. The third objective is to describe radio waves propagation modes such as ground waves, sky waves, and space waves. Now, to proceed with our discussion, let us first understand what is a wave. A wave is a mode of transfer of energy. There are actually two types of waves, which are transverse waves and longitudinal waves. Transverse waves are those whose direction of propagation is perpendicular to both the electrical field and the magnetic field. The electrical field and the magnetic fields lie in planes that are perpendicular to each other, which are x and y planes. Thus, the direction of propagation will be in the z-plane or third dimension. An example of a transverse wave is an electromagnetic wave. Electromagnetic wave consists of magnetic waves and electrical waves. Most of the energy in this type of wave is returned to the circuit. If it isn't, then some of it must be set free or radiated. Radiated energy is not desirable, but if such power is escaped on purpose, then it is said to be radiated. Presented in the screen is an example of wave propagation. Here we can see the direction of electric field, magnetic field, and propagation direction. Here is another example of an electromagnetic wave. You can see here the electric field direction, magnetic field direction, and propagation direction, as well as the wavelength of the wave. Here is another example that showcases light wave in homogeneous medium. Here we can see that an electromagnetic wave is a traveling wave which has time-varying electric and magnetic fields, which are perpendicular to each other and the direction of propagation. Now, let's proceed with electrical to magnetic conversion. In this type of conversion, the antennas are the transducers. Specifically, the transmitting antenna changes the electrical energy into electromagnetic or waves. Then, the receiving antenna changes the electromagnetic energy back into electrical energy. These electromagnetic waves propagate at rates ranging from 150 kHz to 300 GHz. Radio frequency interfaces. If the radiated energy comes from another radio transmitter, then it is considered radio frequency interference. The transmitting antenna should be specifically designed to prevent the energy from being returned to the circuit. It is desirable that the antenna free the energy in order that it might radiate into space. While an electromagnetic interference happens if the energy comes from elsewhere, unlike radio frequency interference, which comes from another radio transmitter. Here is a glance of the terms or definitions and concepts that we will be seeing further. First is the free space. Free space does not interface with normal radiation and propagation. A point source is a simple point acting like a source radiating in all directions. A power density is power per unit area. Isotropic source is one which radiates uniformly in all directions. So, the polarization of the electrical field is determined by the direction of oscillations. If the oscillations are in vertical direction, then the polarization is said to be vertical. If the oscillations are in the horizontal direction, then the polarization is said to be horizontal. Thus, a vertical antenna will result in a vertically polarized wave, and a vertical antenna is one that consists of a vertical tower, wire or rod, usually a quarter wavelength in length, that is fed at the ground and uses the ground as a reflecting surface. A wavefront is a plane joining all planes of equal phase in a wave. When we take a point in space, imagine waves radiating outward in all directions from this point. The result would resemble a sphere. The point of radiation is called the isotropic point source. Isotropic power. Since the power at any point away from the isotropic point is inversely proportional to the square of the distance from the point, then the power decreases rapidly the further away from the point you need. Although the wavefront is curved in shape, from a distance, a small section appear planar and can be thought of as a plane wavefront. Now, we proceed with discussing what is reflection. Reflection is the abrupt reversal in direction. It is caused by any conductive medium such as metal surfaces or earth surface. There will normally be a shift in phase, and the coefficient of reflection is less than 1. For a complete reflection will occur only in perfect conductors when the electric field is perpendicular to the reflecting element or medium. The coefficient of reflection will be 1. Coefficient of reflection is the ratio of the reflected wave intensity to the incident wave intensity. Refraction, on the other hand, occurs when the wave passes from one medium to another whose densities are different. The coefficient is less than 1, and the angle of incidence and the angle of refraction is related by Snell's law. The refraction or bending of signals is due to the temperature, pressure, and water vapor content in the atmosphere. Amount of refractivity depends on the height above ground. Refractivity is usually largest at low elevations. The refractivity gradient or K factor usually causes microwave signals to curve slightly downward towards the Earth, making the radio horizon further away than the visual horizon. This can increase the microwave path by about 15%. Diffractions happen when waves traveling in straight lines bend around obstacles. Based on Huygens principle, each point on a wavefront can be thought of as an isotropic point or a source of secondary spherical energy. This concept explains why radio waves can be heard behind tall mountains or buildings that are normally considered to block lines of sight transmission. Now we discuss attenuation and obstructions. It is said to be that the shorter the wavelength or the higher the frequency of the wireless signal, the more the signal is attenuated. Same wavelength or frequency happens, there is less amplitude, and the longer the wavelength or lower frequency of the wireless signal, the less the signal is attenuated. Presented in the screen is the difference between having shorter wavelengths, having same wavelengths, and having longer wavelengths. Now we proceed with the discussion of the different types of propagation. The first type is the groundwave propagation, which is depicted in the screen. The second type is the skyway propagation, and the third type is the line of sight propagation. The groundwave propagation happens when the curved surface of the Earth's horizon can diffract long wavelengths or low frequency radio waves. The waves can follow the curvature of the Earth for as much as several hundred miles, as depicted on the illustration at the screen. Groundwave propagation results from a radio wave diffraction along the Earth's surface. Primarily, it affects longer wavelength radio waves that have vertical polarization or in which electric field is oriented vertically. Most noticeable on AM broadcast band and the 160-meter and 80-meter amateur bands. Communication distances often extend to 120 miles or more with this type of propagation, and this is most useful during the day at 1.8 MHz and 2.5 MHz when the D region absorption makes skyway propagation impossible. The attenuation related to frequency with this type of propagation is losses increases with increase in the frequency. It is not very effective at frequencies above 2 MHz and very reliable communication link, and reception is not affected by daily or seasonal weather changes, which is a good thing. And this radio wave, this propagation is also used to communicate with submarines, and now we proceed with skyway propagation. But before that, let us first discuss the different atmospheric regions. We have the troposphere, stratosphere, and ionosphere. The troposphere has a height of 7 miles, and this is the region where all weather occurs, while the stratosphere is about 60 to 30 miles, and in this region, where atmospheric gases spread out horizontally, the high-speed jet stream travels in the stratosphere as well. While in the ionosphere, it's about 30 to 400 miles, and this is the region where solar radiation from the sun creates ions, major influence on high-frequency radio wave propagation. Presented on the screen is the atmospheric region with increasing altitude. You can see at the bottom is the troposphere, the stratosphere next to the troposphere, and then ionosphere and the magnetosphere. So what is ionosphere? The ionosphere is the uppermost part of the atmosphere, distinguished because it is ionized by solar radiation. At heights above 80 kilometers or 50 miles, the atmosphere is so thin that free electrons can exist for short periods of time before they captured by nearby ions. This part of the atmosphere is ionized and contains a plasma. In the plasma, negative free electrons and positive ions are attached by the electromagnetic force, but they are too energetic to stay fixed together in neutral molecules. Ionization levels in the Earth's ionosphere can refract or bend radio waves to return to the surface. Ions in the Earth's upper atmosphere are formed when ultraviolet radiation and other radiation from the sun knocks electrons from gas atoms. The ionization regions in the Earth's ionosphere is affected by the sunspot on the sun's surface. Here is depicted on the screen is the things that I've mentioned a while ago. And yeah, this drawing illustrates how radio waves travel into ionosphere and are bent back to Earth ground. Ground waves skip distances. This drawing illustrates how radio waves travel into the ionosphere and are bent back to Earth. Ground waves skip distance and skip zones are all shown on the drawing. So, radio waves radiated from the transmitting antenna in a direction towards the ionosphere long-distance transmission, skywaves strike the ionosphere, is refracted back to the ground, strike the ground, reflect back toward the ionosphere until it reaches the receiving antenna. Skipping is the refraction and reflection of skywaves. The ionosphere In ionosphere, the layers that form the ionosphere vary greatly in altitude, density, and thickness with the varying degrees of solar activity. The upper portion of the F layer is most affected by sunspots or solar disturbances. There is a greater concentration of solar radiation during peak sunspot activity. The greater radiation activity, the more dense the F layer, and the higher the F layer becomes, and the greater the skip distance. So, presented on the screen is the relationship of frequency to the refraction by the ionosphere. Here we can see the critical angle and the angle of radiation. With respect to the frequency and refraction in the ionosphere. Presented in this slide is the relationship of frequency to the critical angle. For point A, which is 20 megahertz. So terms and definitions. So the critical frequency is the highest frequency that will be returned to the Earth when transmitted vertically under given ionospheric conditions. Second is the critical angle. It is the highest angle with respect to a vertical line at which a radio wave of a specified frequency can be propagated and still be returned to the Earth from the ionosphere. The third is maximum usable frequency, or MUF. This is the highest frequency that is returned to the Earth from the ionosphere between two specific points on Earth. The fourth term is the optimum working frequency. This is the frequency that provides for the most consistent communication path via skywaves. The fifth is the quiet zone or skip zone. This is the space between the point where the ground wave is completely dissipated and the point where the first sky wave is received. While fading is the variations in signal strength that may occur at the receiver over a period of time. There are two types of space wave, which are the direct type and the ground reflected type. Presented on the screen is a differentiation or an illustration of difference between direct and ground reflected space waves. We can see that path of the direct wave and the path of the reflected wave. So in a direct wave path, it is limited to line of sight transmission distances. The antenna height and the curvature of Earth are limiting factors to this type of direct space wave. And the radio horizon is about 80% greater than the line of sight because of diffraction effects. Presented on the screen is the radio horizon for direct space waves. We can see the transmitting antenna and the receiving antenna and the limiting factors that affects it, which are the height of the antenna and the curvature of the Earth. So the next type is the reflected. In this type of skywave, the part of the signal from the transmitter is bounced off the ground and reflected back to the receiving antenna. It can cause problems if the phase between the direct wave and the reflected waves are not in phase. Tuning the antenna so that the reflected wave is too weak to receive. So for tropospheric scattering, signals are aimed at the troposphere rather than the ionosphere. 350 MHz to 110 GHz for path up to 400 miles. Received signal is equal to 10 raised to negative 6 of the transmitted power. And there is a fading problem. The third type of propagation is the line of sight propagation. In this type of propagation, radio signals travel in a straight line from a transmitting antenna to the receiving antenna. Provides very high frequency or ultra high frequency communication within a 100 mile or so. Signals can be reflected by buildings, hills, airplanes, and etc. The radio path horizon, distance d to the radio horizon is greater from a higher antenna. The maximum distance over which two stations may communicate by space wave is equal to the sum of their distances to the horizon, as depicted by the illustration presented in the screen. We can see the factors that affect it, such as the curvature of the Earth, the visual horizon, and the radio horizon approximately 15% beyond the true horizon. And we can also see that tropospheric bending happening. So, a type of skyway propagation that allows long distances communication on the very high bands, frequency band, 6 meters, 2 meters, and 220 megahertz, is through the A region of the atmosphere. It occurs only sporadically during certain times of the year. So presented on the screen is the radio spectrum with the symbols or frequency range, wavelength, and comments. So that is the end of my presentation about the topic at hand, and here are the references that I've used for this presentation, and I hope that you understand a thing or two about radiation and wave propagation. That's it. Thank you for listening.